Hello and welcome to this video. Today we are going to discuss how the Pauli degree distributions emerge in the preferential attachment model. The material that I'm going to discuss is based on the book of Remco van der Hofstad, Random Graphs and Complex Networks. We will follow chapter 8 of this book with only very slight difference in notations that I will explain. In our course we have discussed different models that can represent the power laws, for example, configuration model or the generalized random graph. However, these models do not answer the question where the power law comes from, how does it emerge. And the very famous influential paper by Barabasi and Albert has proposed a model that explains the emergence of power laws in complex networks. And the idea is quite natural. The paper says that power law emerged from the Ricci mechanism. Specifically, we assume that when a new vertex arrives to the network, then it connects to one of the existing vertices with probability proportional to the current degree of that existing vertex. So then what happens that a new vertex arrives, looks at the degrees of current vertices, and is more likely to connect to those that already have high degrees. And that is why we call it Ricci mechanism. We can now look at the simulation of preferential attachment and observe how visually that happens. This simulation shows the simplest scenario where every vertex comes exactly with one connection and connects exactly to one existing vertex. So now you can watch the simulation, watch it carefully, observe the Ricci mechanism, and then you can answer a couple of questions of how this model exactly develops. We will now proceed defining the model. And the model that I will describe here corresponds to the model B in the Random Graph and Complex Networks book. So how the model works? Vertex number t plus 1 arrives at time t and makes m connections. Notice that here the set of vertices is denoted slightly differently than in other models. We denote vertices v1, v2, etc. according to the time of their arrival. So we do not denote vertices here like 1, 2, 3 as in other models. And the reason for that is because we want to use this 1, 2, 3 for the time slots, and we wanted to emphasize that this is an object, vertex v1, that arrived at time slot 1. When vertices arrive and form a graph, they create a sequence of graphs. And we introduce notation for this sequence. So this PAT M delta will be the preferential attachment graph at time t. And we look at the sequence of such graphs for all t's from 1 to infinity. Here M is this M, the number of connections, and delta is a parameter of the model that I will explain in a minute. We are interested in the emergence of power laws, and that is about the degrees of the vertices. So we introduce this random variable dit, which will be the degree of vertex I at time t. And here the notations are slightly different from this book. The book uses a notation dit within brackets, but I use it as a sub-index because this is more convenient for the purpose of this video. To make clear how the model works, we start with the easiest scenario that our m is equal to 1, and we have to also initialize the model, and for that we say that vertex v1 starts with m self-loops. So when m is 1, our vertex number 1 creates one self-loop, and therefore it starts with degree equal to 2. And here how model works. We have preferential attachment model with m is 1. So we denote it also here. So in this model with m is 1, vertex that arrives at time t plus 1 connects to the vertex that arrived at time I with probability proportional to the degree of the vertex I at time t plus this parameter delta. And delta is required to be greater than -1 so that this expression is never negative. And this probability has to be normalized so that the sum of all probabilities equals to 1. So here is the overview of the model as we just discussed. And now I want to check that indeed these probabilities sum up to 1. And how do I do that? Of course, the main thing is to sum up the degrees. And if we sum up all the degrees in any graph, then we always get 2 times the number of edges. But how many edges are there? Well, we have t vertices, and each of them has arrived with exactly 1 edge, because m is 1, right? So by the time t, we have exactly t edges, and therefore all degrees sum up to 2t. And this is a 2t here, and all the deltas sum up to t delta. And therefore, if you sum up all these probabilities, you get 1. This is how the model is defined for m is 1. And now we are going to discuss how the model is defined for m greater than 1. So let us now think about preferential attachment with m greater than 1. How can we define this model? What could be a problem? Why do we need to consider it separately at all? Well, first of all, now our vertex arrives and can connect to any other vertex. But the question is it allowed to be connected to the same vertex twice or even more than twice? Can different connections of vertex t plus 1 go to the same vertex I? That is the first question. And assume that this is allowed to connect twice or more to the same vertex. So assume it is a yes, then still there are more options. Should we merge all double edges so that the graph is simple, or should we just continue with the multigraph? Next question is the following. So once one connection is made from vertex t plus 1 to vertex I, the degree of vertex I changes. And the connection probability to vertex I depends on its degree. So the question is, should we update the degrees after each connection or only after all m connections are made? And these choices have to be explicitly defined. In the next slide, I will explain to you how this model is defined in the book. This definition is precise and also turns out to be mathematically convenient. So since our model is very well defined for m is 1, we defined it for m greater than 1 through the model for m is 1. And how we do it, we say, okay, let us consider the vertices arriving with only one connection, right? And we will build a model with m is 1, but we will take delta, which will be delta over m, where m is our actual number of connections that we want to have. So this m. Okay? And this is exactly the rule as we saw before, only with delta replaced by delta divided by m, here and here, all right? And then what we are going to do, we are going to take the vertices that arrived at time from 1 to m, and we are going to merge them all into one vertex, and that will be our first vertex in the preferential attachment model with m greater than 1. Then we will continue building this model with m is 1 and with different delta. And the next the next vertices, the next bunch of vertices from m plus 1 to m, we will merge in the second vertex. And so we continue. Every time the next m vertices of that model are collapsed or merged into one vertex of that model with m greater than 1. And what will happen to the edges? Well, all the edges that belonged to these vertices become now edges that belong to this one vertex. Notice that it is possible that, for example, this vertex connects to, for example, this vertex, and that vertex connects to another vertex of the same batch. So these are all vertices of the model with only one connection per vertex. But that means that we actually have two different edges connecting the same two collapsed vertices. An agreement here is that these edges are preserved. So all edges incident to separate vertices here remain edges of the collapsed vertex. Now, in this construction, what is the probability to connect to this collapsed vertex? That is the sum of probabilities to connect to one of these vertices, right? So then, to compute the probability that we connect to this collapsed vertex, we have to sum up these degrees of all these vertices in this model, and we have to sum up delta over m times. And that's why the probability to connect to the collapsed vertex will be proportional to the degree of this vertex plus delta, as is supposed to be in this model with m greater than 1. I hope you understood the construction. And now remember all these questions, all these choices that we had to make about this model. And now I want to ask you, what do you think in this setting with this collapsed or merged vertices, what choices have we actually made? So try to answer this question and then we will continue. So the two questions we had: is it allowed to connect twice to the same vertex? And the answer is yes. And the choice that we make in this model is multigraph, because these individual vertices from the model with m is 1 are merged together and all edges are preserved. So we can create multiple edges between a pair of collapsed vertices. What about updating the degrees? That's probably a little bit more tricky. Well, again, we first run the model with m is 1, and after that we merge the vertices. So when we run this model, then of course degrees are updated at every step. So that means that when, for example, the vertex, for example, this vertex, when it arrives, then it observes the degree that we have after this vertex arriving. But these all vertices will be joined together. So it means that actually after each connection, the degrees are updated. So now that we understand the model well, we can ask ourselves, were the models like that known or applied before? And it is actually the case, and now I'm going to tell you a little bit more about it. In 1965, Derek de Solla Price has published a very influential paper where he modeled a network of scientific citations. And there also he assumed that a new paper, when it is published, cites an existing paper with probability proportional to the current number of citations that this existing paper has. As an illustration of citation networks, I gave you here a snapshot from the VOS viewer software of Leiden University. Citation networks on our very active area, because using citation networks we can predict development of signs. And apparently power laws also exist in citation network, and that was already predicted and analyzed very long ago by Price, and he used actually the model that is the preferential attachment model. Another example is even earlier by Yule, who analyzed evolution of species. And there also, if we see how many individuals we have of particular species, then we can say that the bigger the population of the species, the bigger there will be offspring, right? So in that sense, this model also has this preferential attachment phenomena. More we have, more we get, rich get richer. But the earliest model that looks very much like preferential attachment was created in mathematics. This is so-called Poyar's urn scheme. So assume we have an urn, and in this urn we have 2 red balls and 4 green balls. And what we do, we take one ball at random. In this case, it was the green ball. We took at random. And if it is green, then we put back that ball and one more green ball, thus increasing the number of green balls in the urn. Now in the next round, when we want to take a ball from the urn at random, the probability of getting a green ball will be higher than before. And this is again that rich get richer mechanism. The more green balls we have, the higher the probability to choose a green ball, and then we will add even more green balls. So this is actually exactly the preferential attachment mechanism, and when we analyze the preferential attachment in complex networks, then we also very often use the mathematical machinery developed for Poyar's urn scheme. That said, the contribution of Barabasi and Albert is very significant, because they realized that there is this universal phenomena of scaling power laws emerging in complex networks, and they related it to the preferential attachment mechanism and popularized it considerably, made it very substantial and very influential model in network science. And it is not for nothing that this paper has more than 42,000 citations in Google Scholar and counting. The preferential attachment model is now a very important model in network science, because not only it has power laws, but it also explains how power laws appear. So in the rest of this video, we are going to discuss why exactly mathematically this preferential attachment mechanism results in power laws. So now we will focus on the question how the power law emerges, and to make things simple, we will take delta is 0. We will also simplify it a little bit further. We will say, okay, assume that a vertex arrives with m connections, and we will simply say that each of the connections of this vertex t plus 1 may go to vertex I with probability proportional to the degree of I. Strictly speaking, in this model, we have to put approximate here, because recall that if a vertex arrives with m connections, then the degrees are updated after each connection. So if a vertex arrives at time t plus 1, then the equality here will hold for the first connection made by this vertex. But after that, the degrees will be updated, so the strict equality will not hold anymore. However, when the network is very large, then it will not matter, because we will have a lot of vertices, a lot of connections, so the update of the degree after these connections will not matter that much. And that's why we just assume that this formula holds. And then again, the probabilities will sum up to 1, because if we sum all the degrees, right, all the degrees, then we will get 2 times the number of edges. And what is the number of edges? Well, each vertex arrives with m edges, and there are t vertices, so there are in total tm edges, and this 2 is that 2. Therefore, these probabilities sum up to 1. So now we will derive the power law using recursion. And for that, we introduce that quantity, nkt, that will be mean or expected number of vertices of degree k at time t. And our approach will be the recursion. So we are going to write an expression for nkt plus 1, starting with nkt and then looking at the difference. That will be our first step. So let us see how to do that. Now the first thing that we have to compute is the expected number of new vertices of degree k at time t plus 1. This is an expectation of some count, and for that, as usual, we will use the sum of indicators. So what will be the sum and what will be the indicator? Now, assume that a vertex arrives at time t plus 1, so this is our vertex t plus 1, and it has m possible connections. So, m connections. Let's number these connections from 1 to m. Now, when can we get a new vertex of degree k? We get it when one of these connections goes to the vertex of degree k minus 1. So then, what is then the count of such new vertices? We have to then sum up over all connections for s from 1 to m, and the indicator will be of the probability that connection s, over which we sum, goes to some vertex of degree k minus 1. Then this vertex of degree k minus 1 will receive this extra connection, connection s, and it will become a vertex of degree k. So the expected number of new vertices of degree k will be expectation of the sum of indicators. Let us now continue. The expectation of a sum of indicators is simply the sum of corresponding probabilities from s from 1 to m, and then the probability of this event, then that connection goes to the vertex of degree k minus 1. For each vertex, we know that the probability to receive a connection is this, proportional to the degree, and in this case, degree is equal k minus 1. Then this probability will be proportional to k minus 1, right? And we have to divide by 2tm, that is coming from here, right? But we also shouldn't forget that the connections goes to some vertex of degree k minus 1, and this is only the probability for one of them. But we have many of them. In fact, on average, we have n k minus 1 t of such vertices. So then this expression will be equal to that probability. And we have to sum up this probability m times because of this summation. So we have to multiply this probability by m because this probability is the same for each connection. So now let us write down the formula. This will be equal to, now first m, this m is coming from here, and then we have to multiply by this expression, so that will be k minus 1 divided by 2tm and multiplied by n k minus 1 t. And here is a very nice thing happens, because this m magically disappears, it cancels. And now we have to take this expression and substitute it all the way over here. We are going to rewrite it now. So now let us look back. We want to derive the mean number of vertices of degree k times t plus 1. We have it what it was, plus we have some new vertices of degree k which appeared because for some vertices of degree k minus 1 have received new connections. So this is our expression so far. And my question is now, are we done? Is it all, or should we still continue? Now think about it, answer this question, and then we'll continue. So this is the entire recursion. This is a term that we have derived in detail, but this is not all. Because besides the fact that vertices of degree k minus 1 will receive new connections and get degree k, also what will happen that the vertices of degree k will receive new connections and they become vertices of degree k plus 1, and therefore the number of vertices of degree k will reduce in this way. Therefore we have to subtract the similar expression exactly as here, but for k, for the vertices of degree k that receive new connections. Now we will use this recursion further to derive the power laws. Now this slide has a lot of formulas on it. Let us look at it. So this was our original definition. That was it, right? And that was the recursion that we derived so far. Okay. Now, what I did here is I wrote similar recursion, but for vertices of degree m. The vertices of degree m are special because how many of such vertices we will have at time t plus 1? Well, we had what we used to have, right? Plus, at every time t plus 1, there will be one vertex arriving, and this one arriving vertex will have exactly degree m. Therefore, this one we always have to add. However, what also will happen, exactly as here, some vertices of degree m will receive new connections, and they will become vertices of degree m plus 1. And that's why we have to subtract this term exactly as we did before. So now, together, these two equations constitute an entire recursion for these quantities. And from this, we are going to derive the power law. To do that, we have to go from the number of vertices, like here, the mean number of vertices, we have to go to the probabilities, to the fraction of vertices of degree k. So we introduce this fraction, so this pkt will be the fraction of vertices of degree k. And what this fraction is, well, we have to take the number of vertices of degree k and we have to divide it by the total number of vertices. And we know that at time t we have exactly t vertices, and therefore pkt is an average mean fraction, because it was mean number of vertices, it will be a mean fraction of the vertices of degree k. And now I'm going to rewrite these two equations in terms of pkt. Okay, let us do it. So first of all, this nkt plus 1 is nothing else but this pkt plus 1 multiplied by t plus 1. So that is replaced. This is replaced by this. Then what we do, we take this nkt and we take it to the other side with a minus. It is this one. And this nkt is simply t times pkt, and taken to the other side. Now, what happens here? Here we already have this nk minus 1 t divided by t. So that becomes this pk minus 1 t by definition, right? This is actually n divided by t, and this is p. And the same happens here. So this nkt divided by t becomes this pkt. And therefore we have now recursion for p instead of n. And exactly the same thing we do for this recursion for m. So n1 stays here because nothing happens to 1, right? The only thing we do, instead of variables n, we substitute variables p according to that rule. You can pause the video and look a little bit at this recursion, because it takes some time to understand how to go from these variables to these variables, but actually the calculations themselves are quite straightforward. Okay, here again are our equations for the p's, and now what we want to do, we want to know what happens to the fraction of vertices of degree k when the network is large, so when t goes to infinity. So we are letting our t go to infinity, and we assume that our probabilities will converge to some limit. And if this is the case, then this t will play no role here, right? So if probabilities converges to the limit, then we can forget this t, and we can forget this t, and then what we see here is that here is t plus 1 pk, and here is t pk, so when we subtract, we have this 1 pk difference. So this 1 pk from here will be here, and on this side, we just say, okay, forget this t, and then from this side, we get this expression. So by taking the limit, we obtain this limiting recursion. And the same happens here for the m. Important point here is that we do have to take into account that here we have t plus 1 and here we have t. And even if t goes to infinity, still this t pk and t pk will cancel, but this 1 pk will remain. And that's why it remains here. And the same, of course, for pm. Okay, this is actually quite an easy recursion. And why is it easy? Because we can already see that we can solve this expression for pm. We can simply find pm from this equation. And once we found pm, then what we notice that we have this pk always dependent on only pk minus 1. So we have here pk and pk, and we can express it through pk minus 1. So once we know pm, we can obtain from this expression, we can obtain pm plus 1, pm plus 2, etc. for any k we like. We can solve this recursively. These equations are very well known, and in physics they are often called master equations, or in mathematics they are often called balance equations. These are the equations that connect different probabilities that describes the system in the limit or in the equilibrium. Now these are only calculations. These are our equations again from the previous slide, and I have solved it recursively as explained before. First I solved it for pm, and this is my expression for pm, and then I expressed this pk through pk minus 1, and this is my expression pk as a function of pk minus 1. And we see that this is very simple expression, and that is simply because these recursions are linear recursions, so they are very easy to solve. Now, from this recursion, you can already understand what you have to do next. You have to express pk minus 1 through pk minus 2, then pk minus 3, etc. till you reach pm. You can try it yourself, and I will write for you the results in expression on the next slide. Okay, so here I have rewritten pm as it was, and for pk, I have substituted pk minus 1 and then pk minus 2 recursively, and I have arrived to this pm. This is the results in expression. And what I notice here is that from the very first recursion, we could already see that I have here k minus 1, and here I have k plus 2. And actually this all was pk minus 1. So we see this difference of 3 appearing here, and this difference will not go away. So these first three terms, k plus 2, k plus 1, and k, they will not cancel. The first term that will cancel will be the next one, k minus 1. It will cancel here. But also here the last three terms will not cancel because, again, for the difference of 3. However, m plus 2 will cancel from here because of pm, because pm is 2 divided by m plus 2. So when we substitute all this, then we get these three remaining terms. They remain, they cannot disappear. And out of these three last terms here, m plus 2 will disappear because of pm, and 2 will appear also from pm. This is these two. Okay, and then this will be our resulting expression for pk. And now m is fixed, m plus 1 also, so we can take it outside. And also we can take outside k to the power minus 3. And what will remain in brackets is something of the order 1 plus of 1 over k. So that will be vanishing in k. And that is, of course, already our power law. So we have obtained a power law here in the limit. And in this case, we have τ equal to 3 because of this power of 3 here. And this is how the power law results from the preferential attachment model. Now we can do a similar derivation for a more general case where we do have delta, where delta is greater than minus m. And of course here again for the same reason it actually will be approximately, but it wouldn't matter for that derivation. And my question to you now, what do you think? Will the delta affect the power law exponent? Will we again get τ equal to 3, or will we get a power law with τ that depends on delta? So think about it and then I will give you the answer. Now if you repeat all the calculations, then you will see that delta actually matters. The power law exponent is now minus 3 minus delta over m. So this is our new τ. And you can derive it in exactly the same way, but instead of products there will be gamma functions appearing, and you will need to use equation 839 in the book. The τ can now be anything between 2 and infinity. We can get close to 2 if we take delta to be negative. When we increase delta, then τ also increases, and that means that very large degrees become less likely because this power becomes a greater negative power. So does it make sense? Now suppose that delta is positive and delta is large, then it smoothens everything out. So it will become harder for the vertices of very high degrees to get more connections, because this large delta will make distribution more uniform and will help the vertices with small degrees to compete. And that's why when delta is large, it will be harder to see really huge degrees. So this is an overview of our derivation of a power law when delta was 0. This is just the steps repeated as we did them before, and I have identified 5 steps that we made. My main point here is that this is so-called heuristic derivation. It means that at least some of these 5 steps are not mathematically precise. So we made some steps that were intuitively reasonable, but not completely mathematically rigorous. And my next question to you is, which of the steps were not rigorous and why? Now let's see where we didn't make it rigorous. Now, first of all, when we were making this recursion, then we derived this expression, and here with this we have ignored that the degrees are updated after each connection. The next point is more tricky and is often overlooked. we have assumed that these n's, all these n's, and all these p's are mean values. So it is a mean number of vertices of degree k and the mean fraction of vertices of degree k. But when network grows, then it looks at actual number of vertices of degree k, and this number is random. And since this number is random, this fraction is also random. And in this equation, whether this random number of vertices of degree k, a random fraction of vertices of degree k, are actually close to their means, and where the equations for the means reflect the dynamics for the actual number of vertices of degree k. So that is the next non-rigorous step that was in the first step, and in the second step it played a role as well. Now next, usually students identify easily step 3. It is not justified that we can take this limit. We do not know whether this limit exists. So intuitively it is clear, but it is not mathematically rigorous step. Now next, about solving the recursion. Actually here everything was fine, and this solution is rigorous, and this transition is also fine. Now the natural question is, how can we make the proof rigorous? The book explains it in detail, and I will give you only an overview. I will first explain to you how the result is presented in the book, and after that I will explain to you the plan of the proof. So to make everything rigorous, we have to be honest. We have to say nkt will be the random number of vertices of degree k at time t. And then we create a fraction, which is simply the number of vertices divided by t, and that is also a random variable between 0 and 1. Notice that pkt that we had in our heuristic derivation are approximately expectation of actual capital pkt because of the non-rigorous steps 1 and 2. That's why it is an approximate and not precise. And now what will be the statement, how the statement is formulated? It actually says that if we take this random fraction of vertices and we compare it to that solution pk that we have derived, and we look at the difference between the random fraction and the solution that we derived, and we take the maximum possible difference over all k's, then the probability that this maximum distance will exceed something of the order square root of log t divided by t, that probability goes to 0 as t goes to infinity. And notice that log t over t goes to 0, so actually the difference between these two numbers with high probability will be small and will be vanishing. I hope this result is clear, and now we will only briefly look at the general plan of how something like that can be proved. So here is a statement again, and this is an overview of the proof. What we do is the following. We take this difference and we use a triangle inequality to split it up. We subtract expectation of pkt and add expectation of pkt, and now we look at the difference between pkt and its expectation and between the actual expectation of pkt and those pk's that we have derived. And then for each of these two parts we prove separate propositions. Proposition 8.4 tells us something about the difference between pkt and its expectation. And for those who are interested, I can say that it is using Azuma's inequality, concentration inequality for martingales, and pkt times t is proved to be a martingale, and then it's compared to its mean. And this square root from logarithm t divided by t comes from those concentration inequalities for martingales. But in any case, it is proved at least that this part exceeds this expression with vanishing probability. And then for this part, we have to compare some equations. So basically, expectation of pkt is a deterministic quantity, so are the pk's. So now we have two deterministic quantities, and we derive actual equations for expectation of pkt. They are much more messy than those that we saw for the pk's. And then we prove that these two sets of equations are actually not very different. And that's how we can prove that the difference between expectation of pkt and pk is actually of the order 1/t. And then we combine both of these results to conclude that the entire statement holds. I do realize that still it doesn't help you to prove the theorem if you want to prove it by yourself, but I hope it gives some impression of what are the steps and what are the techniques that you may need if you want to prove a result like this. This is a very nice assignment for two reasons. First, you can check whether you understood how to make this heuristic derivation for pk by repeating the argument in a different model. But another interesting thing is that this model in this assignment is so-called uniform attachment. That means there is no preferential attachment. A vertex arrives in a network and connects to any other vertex with the same probability. So no matter what degrees they have. And of course, in this case, I can already give some spoiler, you will not get a power law. And that will allow you to see that actual preferential attachment, when degrees play a role, results in power law, while uniform attachment that doesn't have this influence of degrees does not produce power laws. I wish you a lot of success with solving this, and I hope it will not be too difficult after all the explanation that we had. Good luck, and thank you very much for your attention.